There we go. We know how to do stuff like this, right? We know that we could take, for example, a right sum by just taking the limit of the sum of f of a I delta x, all times delta x, as I goes from 1 to n. And you're practicing that, right? In the limit as well, it's not supposed to be an x, it's supposed to be an n. As n goes to infinity, right? Well, there is one more general way to write this, and this is the way typically you'll see a Riemann sum written. So what's all this nonsense? Well, this is just saying C sub I just means C for convenience. So C for the use the most convenient value of x to define the heights of the rectangle. So what's that going to be? I mean, it's going to be the right edge, isn't it? Right. So that's typically going to be C sub I is just going to equal a plus I delta x, just like we were using, right? So we were doing it the most convenient way. What is this thing right here? This thing right here is what we call in calculus the norm. And it's just meant to represent the widest of all of the subintervals. So if the widest of all of the subintervals is going to 0, then we're going to fit the curve perfectly, right? How have we dealt with that? Well, we've always dealt with that by just letting all of the subintervals be the same width, and then letting the number of subintervals go to infinity, right? Why would you ever do this? Well, there are some instances where it's not convenient to let all the subintervals be the same width. Like if you were finding the area under a radical, for example. And I'm not going to drag you through an example of this. I don't really want to make you experts at finding limits of discrete sums because we really don't do that very often. In the past I've shown some examples of that, but I don't think it's really necessary. I mean, if you're a math major, let's have everybody. I want all the earbuds and stuff away, please. So, I mean, I just want everybody plugged in here. Thanks. So, I mean, plugged into me and what was going on up here, not plugged into something else. So, there are some cases where we don't want to use uniform width subintervals, and in that case, this is the way that we write it. So, I mean, if we were letting our subintervals be, for example, the width be proportional to x or something crazy like that. Well, we still have to find a way to let whether it's letting, the number of them go to infinity like we've done or using some other mechanism. We've got to find a way so that the widest of all the subintervals goes to 0. And in that case, this is still going to work. If we do that, though, notice that we need to index the widths of the subintervals because now we're not assuming they're all the same. Here, they're all the same. Right? Delta x is just defined as b minus a over n. Here, no. Here they could vary in width. So this is the most general way of stating it. Does it change anything we've done? No, not really. Because I'm only going to give you examples where you can use uniform width subintervals. If you're a math major and you go on and study, calculus at a higher level, then you'll have an opportunity to go back and become better at this process. But you rarely, if ever, do that. It's very, very rare. Because we're going to come up with a trick that's going to work. It's a lot easier to use. And in the few instances we'll find here in the fairly near future where the new process we're going to develop fails, and it does in a couple instances, because there's certain kinds of functions where it fails, we're going to use a better, more efficient way of approximating areas under curves. Okay? And this wouldn't work anyway. I mean, in that case, you can't take a limit as n goes to infinity, for example, in those cases where the process we're about to establish fails. Unfortunately, you can't find an exact area under the curve, and so you simply have to do an approximation, but we'll find more efficient ways of doing approximations than rectangles. Okay, when we get to that point. But that's in the future. For now, let's just focus on trying to come up with a more efficient way than having to take limits of discrete sums, because that's a fair amount of work, right? Let's take an example. Let's just look at the area under the function f of x equals x, on the interval from A to B, okay? So we can fit that to our current process. Here's what our function is, right? We're letting, we're not gonna specify what the endpoints are, and you'll see why. What's this gonna look like? So let's just start, here's our general expression of our Riemann sum. Let's get specific, okay? So, what's it gonna look like? So what is f of hand gonna be in this case? F of hand equals hand, yeah, right? So our area is equal to the limit as n goes to infinity of just the quantity a plus I delta x times delta x, right? The sum of that, sorry. Sum of that as I goes from 1 to n. What's delta x?
A minus A over 2.
B minus a over n. There we go. So we could write this. That look good? What we could do here?
Take the B minus A over 2.
Yeah, okay, good. The B, there are no i's in that factor, are there? So we can factor that out in front of the sigma, pull it out front, right? So we could write this as the limit as n goes to infinity of b minus a over n. Now I have an n in it, so it's still subject to the limit, right? Of the sum of all this stuff. A plus b minus a over n times I as I goes from 1 to n. Okay, now what?
Distribute the summation.
Say it again.
Distribute the summation.
Okay, so I could, by distribute summation, what do you mean, like break this into
Break
two
it
Yeah,
parts?
break it, yeah.
Okay, yeah, we could do that. So we could break this into two different sums, couldn't we? Because I've got a plus sign here. So I'm just gonna sum this term by term, right? So we end up with the same stuff out front. I'm gonna be really tricky here, save myself a little. It wasn't that tricky. So there's that guy. And then I've still got my, well, then I'm gonna have in, let's put it in square brackets, the sum of A plus the sum of all that stuff, right? And the B minus A over N I could pull out in front of the sum, couldn't I?
Can you go a little bit?
Sure. Right, so if I break this into separate sums, when I get to this bottom sum, the sum of this part, the B minus A over N, I could put out in front of the sum. Let's do that. Right? And those sums are all from 1 to n, okay? So what's the sum of A from 1 to n?
And
A n, okay. So we get this whole thing just becomes an plus b minus a over n times, what's the sum of I? Come on, Dad.
it's
N
n
times
plus
n plus 1 over 2.
Okay. Marcia, good? Okay, any suggestions here for our algebra?
Cancel out the n.
Cancel some ends. That works well. Right? And, so new page. Then what?
multiply the b minus a.
Okay, I could do that. I'm gonna do one thing here that I think is gonna be helpful. I'm just gonna multiply the 1 over n through. Okay, first, and we'll get to this other part. What's that gonna do? So if I distribute that 1 over n,
It's gonna make the a.
I'm just gonna get an a from that term, plus b minus a times, if I multiply by 1 over n, I'm gonna lump the 2 with that. What is n plus 1 over n gonna look like?
N over n plus 1.
Right, so I'm gonna get n plus 1 over n, which just becomes, if I split those fractions,
1 plus
1.
okay, does that make sense? How many n's do I have left?
1.
1. So I can take my limit, right? As n approaches infinity, if I take the limit, what happens to the only term left with an n in it?
Goes to 0.
Yeah, it goes to 0, doesn't it? Right? So it goes away. So then I'm left with an answer that only involves a's and b's, which seems pretty good. So we end up with then b minus a times a plus b minus a over 2. So we've just got to simplify that a little bit is all, right? Okay, so what might that look like? Well, what is a plus b minus a all over 2?
Delta x.
Okay, but not exactly, but this is really like 2a over 2, right? Everybody agree?
It's so fun. It's just
Ah, okay, good. So I'm gonna get, so if I just make that 2a over 2, I've got a common denominator, then what's gonna happen inside those brackets?
Plus b.
I've got a 1/2 there, don't I? I'm gonna end up with 2a plus b minus a. That's the same thing as a plus b, isn't it? Right?
Yeah.
Would agree? So I end up with a plus b over 2, right? And now what if I multiply through by b minus a? I could also write this as b plus a. In fact, let me do that. Not that it matters. I mean, addition's commutative, right? So the order doesn't matter. What's b minus a times b plus a? That's that conjugate pattern.
b squared minus a squared over 2.
Which I could write as, if I wanted to, b squared over 2 minus a squared over 2. Okay, so can you connect this to my original function? So the original function was f of x equals x, right? And I ended up with b squared over 2 minus a squared over 2. The challenge is to find a connection. I'm going to give you one little hint. Another way to write this would be to say, okay, it's the same pattern for b and for a there, isn't it? Right? It's b squared over 2 and a squared over 2. So we could write this, if we wanted to, we could write this as x squared over 2 evaluated from a to b, which means this is a new notation for you, but this means this expression evaluated at b, the difference of this expression evaluated at b and a.
Why would you give the subtraction part?
That's just what this notation means. This notation means this expression evaluated at b, so it's going to be b squared over 2 minus this expression evaluated at a.
Is there one of
And
those?
you could put an optional bracket on this side if you want to. But even if you just have half a bracket, that's a new notation for you, but that's what it means. Okay.
Is there one for addition?
Not really, not a common. And you'll see why. This one was invented specifically for this application that we're working with right now. So if our answer looks like this, and we started off with the area under the function f of x, do you know of a way to connect f of x equals x to x squared over 2?
Isn't that the antiderivative?
It's the antiderivative. Yeah, isn't it? Right? That's the antiderivative. Could that be an accident? It's not. Right, so we know that the antiderivative of x dx, and there's my function, right, equals x squared over 2,
No, plus
right? So when we asked to find the area under the curve from a to b, look what we ended up getting. We ended up getting the antiderivative of the function evaluated from a to b. Okay? That is a great shortcut, right? So it gives us something, this gives us a new trick. This is what we call a definite integral. And this is the first fundamental theorem of calculus.
So we don't. So with these, we won't have to put plus c.
No, these are different, right. And we'll talk about that. So if we want to find the area under f of x from a to b, then here's what that means. It's going to be the integral of f of x dx from a to b. These are what we call the limits of integration, and they mean the boundaries of the area under which we're adding up an area. Okay? And we would write this as, the answer as f of x, where capital F of x is our antiderivative, evaluated from a to b, which is simply the antiderivative at b minus the antiderivative at a. Okay? So this is, it's bizarre that it works this way. This is a definite integral, and it stands for an area under a curve. An indefinite integral, which we've always called an antiderivative, is something totally different. It's a family of curves whose derivative is that, right? Pretty bizarre. And we'll go look back on this and say, okay, why did that work? And we'll come up with an explanation. But for now, it's just a great shortcut. So what if we wanted to add up? There's our first fundamental theorem of calculus. What if we wanted to add up an area under, oh, how about this? What's the area under f of x equals the square root of x from 1 to 4? We would have had a really hard time doing this the old-fashioned way. The old-fashioned way being what we did yesterday, right? Using limits of discrete sums. That would have been really tough to do. But we have a new trick. How do we set this up? Yeah, so this is just going to be an integral of from 1 to 4. Good, there's our limits of integration of,
X to the 1/2 dx.
yeah, of x to the 1/2 dx. Okay, well this is pretty easy. What's the antiderivative of x to the 1/2?
2/3 x to the 3/2.
Good, 2/3 x to the 3/2. No plus c this time though, right? The two, you see how we got 2/3, because it's x to the 3/2 over 3/2. We just flip and multiply. Evaluated from 1 to 4. Okay? Now, there's two roads we can take here, two routes we can take. We could say, let's just evaluate this whole thing from 1 to 4, right? And what's that going to give us? Well, that's just going to give us 2/3 times, what's 4 to the, let's write it that way, 4 to the 2/3 minus
This is 3/2.
3/2, whoops. Minus 2/3 times 1 to the 3/2. Well, what is 4 to the 3/2? That's just 4 to the 1/2 cubed.
8.
8. 4 to the 1/2 is 2, right? Square root of 4. Cubed is 8. 8 times 2/3
16.
minus, what's
It's gonna
1 to
be
the
2/3.
3/2?
1.
1.
So it's going to be minus 2/3.
So we end up with, what, 14/3? Okay. Is there one other little thing we could have done here that might have been a little bit more efficient? You see anything like right here that we could have done?
Just taking out 2/3.
Yeah, we could have factored out a 2/3, couldn't we? Right? We could have pulled the 2/3 out in front because it's a constant. Factored it out of each of those two. All we're doing is factoring it out of the two terms, right? So we could have written this as 2/3 times x to the 3/2 evaluated from 1 to 4. So 2/3 times 8 minus 1. 2/3 times 7 is just 14/3. Okay? So once again, sort of the anatomy of a definite integral. So let's see. So our Riemann sum can just be written as the integral from a to b of f of x dx, and it just equals the antiderivative from a to b. Okay. So this is what we call, these are the limits of integration. This is the upper limit. The lower limit. So just like before, that's the integrand. And this is nothing more than antiderivative. And so we'll come to think of this as an area function. We'll talk more about that later. And, you know, once again, it's don't overlook the vast difference between a definite integral and an integral. What is the answer to a definite integral going to look like? Yeah, it's an area. Definite integral is an area. Right, so it's always, what's our answer going to look like? It's a number. Yeah, it's a number, right? Because it's an area. I mean, it's a calculated area. Yeah.
It's always gonna be positive.
Is it always going to be positive? No, it's not. That's what we're talking about next. It doesn't always have to
Can
be
you go
positive.
back?
We have to define our area conventions, but that's easy to do. It's no big deal. What if we don't have the limits of integration and it's an indefinite integral or an antiderivative? What's the answer look like there? Like if we had done instead, we did square root, right? What if we had instead just done what would our answer have been? So you already told me the 2/3 x to the 3/2 plus c. It's a whole family of curves, right? Infinite family of curves, right? And we can solve. We've done already some work solving differential equations where we're given some initial conditions and we can solve for the value of the constant, pick out one trajectory out of that family, right? They're totally different. I mean, it's not a number. It's either a family of curves or if we're given some additional information, a single curve, right? Okay, so let's explore what this area that we're talking about. We're adding up areas under curves. So let's do something like, something easy. Let's do something like, how about the area, let's take a function like x cubed. Okay, we all know what x cubed looks like. It's got odd symmetry. Looks like that, right? That's f of x equals x cubed. So let's add up the area, how about under x cubed from 0 to 2. Okay, what's that going to equal?
X cubed or x to the fourth.
X to the 4th over 4, right? So we're playing Jeopardy with this, remember? X to the 4th over 4 evaluated from 0 to 2, which is just going to be 2 to the 4th over 4 minus, what's this going to be at 0? 0, right? So that's just going to give us, what's that going to be, 16 or so 4? Okay, so this area up here, out here, it's not drawn to scale, but from 0 to 2, we got some positive area up there. Okay. What if we do the area from, same thing, x cubed dx from -2 to 0? Same thing? Well, let's just, for kicks, let's just do this. So we end up with x to the 4th over 4 from -2 to 0, right? So that's going to give us, let's see, at -2, we're going to, we're going to get, we're going to start at 0, aren't we? Right? So we're going to get 0 minus 4 equals -4. Why is that negative?
So it's under.
Exactly. Yeah, that's negative because it's below the x-axis. That's the reason, right? So when we talk about area, you know, we haven't really gotten into how we define area yet. We've only done examples where it's been positive, but area is defined. When we talk about area under a curve, what we really mean by under is the area between the curve and the x-axis. If the curve is below the x-axis, then we're actually calculating negative area, okay? If it's above the x-axis, we're calculating positive area. So what do you think if we combine these two, what do you think we're going to get if we take the integral of x cubed dx from -2 to 2?
0.
It's going to be 0. It is going to be 0, right? And look at what we get. We get x to the 4th over 4 evaluated from -2 to 2. Well, that's going to be 2 to the 4th over 4 minus -2 to the 4th over 4, which is 0. Right? Everybody agree? Okay, so this is, would you agree that f of x equals x cubed is an example of an odd function? Right, what's our test for an odd function?
It's
How does that work if we f of negative x equals, but just in general, for an
A
odd
negative
function, f of negative x equals negative f of x, right? So if I go over by some amount x, I'm going to go up yay far. If I go backwards by negative x, I'm going to go down yay far, right? So the y value is going to be opposite, right, of what it was at positive x. Okay, so for an odd function like this then, can you come up with a general rule? There's a shortcut here, right? For an odd function, if we remember that a definite integral is really just adding up an area under a curve, what would happen if we took any odd function and we integrated over symmetric limits of integration? So from -a to a. I'm going to get 0, aren't I? Right? That's always going to be true. Right? So if we've got something like, if f is odd, then the integral of f of x from -a to a, whoops, dx, has to always equal 0, doesn't it? Make sense? Okay. Can you think of a shortcut for doing something like this? What if we wanted to add up okay, let's say we wanted to do the integral of x cubed dx from -1 to +4. Could you write that in terms of another integral that has the same area with smaller limits of integration?
0 to 3.
Not 2 to 4. 1 to 4. Yeah. Think what? Let's look at the picture. I'm not going to draw this to scale, but we've got,
Oh yeah, because the
right? So let's break this into parts. Let's say that's -1, +1, 1, 2, 3, 4, right? So look at this area here. This area right there and this area right there are going to cancel, aren't they? Because those are over symmetric limits, right? So they add to 0. So then this area from there to there is what's left over, right? We could be tricky with that, couldn't we? So we could write this as the integral of x cubed dx from +1 to 4. They'd have to be equal, wouldn't they?
That doesn't necessarily make it easier.
It doesn't in this case, you're right. It doesn't in this case. But it's in the future it might, in some cases, make things easier, okay? But that tells us something else then too. We just, by implication, that's also giving us another area property, right? That's implying that if I have the integral of some function from a to b plus the integral of the same function from B to C, what must that equal?
Integral A to C.
Right? Does that make sense? Okay. So now I got another mind bender for you. Not mind bender. I got another. So if that's true, right? And that's generally true. Then what about something like this? What if we want to do? How much time we got?
5 minutes.
5 minutes. Okay. So yeah, I'm not gonna. We'll do this the quick way today. So what if I want to add up? Let's say that I know that the integral from -2 to +7 is equal to 13. And I know that the integral from +3 to +7 equals 9. Okay. So then, what must the integral from -2 to +3 be equal to? It has to. Everybody agree?
Mhm.
It has to equal 4, right? Okay. Because what's your reasoning? Well, I would assume from -2 to 3 joins up with from 3 to 7. So 4 plus 9 equals 13, right? Okay, but this should also work for me to say, this. I should also be able to say, now watch this closely. I should also be able to say the integral of f of x dx from -2 to 7 plus the integral of f of dx from 7 to 3 must also equal the integral of f of x dx from -2 to 3, right? Agreed? Because all that has to happen is the upper limit of my first integral has to match the lower limit of my second, right? Okay, now think about these. I know that this guy right here is equal to 13, right? And I know that this guy right here is equal to 4. So then what does that tell you about that integral?
It's negative.
It's negative, it has to be -9, right? How come it's -9? Because look, we defined the integral from 3 to 7 as
Is
positive.
it because it's
It's opposite, it's
Invert.
going
Because I flipped the direction, right? So I'm adding up the area from 7 to 3. I'm adding up the area backwards. Okay, so that tells us something else really significant, right? That tells us that the integral of f of x dx from a to b is the opposite of the integral of f of x dx from b to a. So there's another area convention. What are our conventions? Well, we assume that we're adding up area above the x-axis as positive, and we assume that area added from left to right is positive. If I add area from right to left, that's negative. I'm going backwards.
so you could have a positive area under the x-axis.
If you're adding it up backwards. Right. Yep.
Can you go back?
Sure.
How did you get, the 9?
I just made it up. I just said, you don't even know what f of x is in this case. I'm just saying there's some function, and the area under this curve from -2 to 7, I'm just telling you it's 13, without even knowing what the function is, right? The area from 3 to 7 is 9, so you told me immediately that the area from -2 to 3 is 4, and you're correct, right? But what that allowed us to discover is if we mixed up the orders in which we added up those areas, this has to be a true statement, right? And so that tells us then that when we flip the limits of integration, it changes the sign of the area, okay? That's, for those in physics, here's an example of why this stuff becomes important. I can't resist. Oh, I can't. 1 minute. We'll do it in physics today. Because we could tie this into work in a really interesting way. All right.
Thing that